Current large language models operate on a specific mechanical standard. They ingest text, break it down, and predict the next discrete subword from a fixed vocabulary, scoring accuracy through cross-entropy loss. Because this architecture processes data strictly sequentially, piece by piece, it lacks a mechanism for explicit, higher-level abstract planning. The model is constrained to the immediate, microscopic level of individual words. Human cognition operates top-down. When structuring a speech, we don't calculate it word by word. We draft the flow of abstract ideas first. High-level concepts are organized and mapped out well before those ideas are instantiated into a specific language or vocabulary. Achieving human-like long-form reasoning in artificial intelligence requires a structural shift. The discrete token bottleneck must be bypassed to allow for a hierarchical semantic architecture. Meta Fair recently published a proof of concept for this kind of hierarchical machine reasoning. They call it the Large Concept Model. The core mechanism of the LCM moves away from token-level processing. Instead, the model's fundamental operational unit is what the researchers term a concept. Within the scope of this study, a concept is defined mathematically as the continuous, high-dimensional semantic embedding of an entire sentence. Rather than estimating the probability of a discrete text token, the LCM auto-regressively predicts the continuous semantic vector representing the next logical sentence. By shifting prediction from a fixed vocabulary index to a continuous semantic space, the model targets the underlying representation of an idea rather than its specific textual assembly. To predict concepts at this level, the LCM requires a highly semantic, modality-agnostic latent space to operate within. This diagram illustrates the SONAR embedding space. It compresses a full input sentence, regardless of language or modality, into a single, continuous vector. First, input is segmented and passed through the frozen SONAR encoder, generating an array of concept vectors. In step 2, the LCM core contextualizes this sequence and auto-regressively predicts a new continuous vector for the next concept. In step 3, a frozen SONAR decoder translates that vector back into human-readable text tokens. Throughout this process, the LCM core never sees raw text. It strictly ingests and outputs abstract mathematical representations of meaning. By relying on frozen external encoders and decoders, the LCM's internal reasoning engine is decoupled from the input and output modalities. Operating in an infinitely continuous space introduces a severe engineering challenge. The standard method of using a discrete softmax distribution no longer applies. Researchers first tested a base LCM architecture. They trained a standard transformer to predict the next concept vector by minimizing mean-squared error against ground truth. This approach fails because language generation is highly multimodal. A single context can easily have many valid, distinct continuations. Mean-squared error penalizes distance equally, forcing a compromise. The model ends up predicting the arithmetic mean of all plausible semantic futures. This averaging effect causes the predicted vector to land in dead space. The resulting coordinate does not correspond to any coherent linguistic meaning. The empirical evidence is clear. The base LCM shows degraded contrastive accuracy and mutual information scores compared to generative methods. Successful autoregression in a continuous latent space requires a mechanism capable of sampling distinct, specific semantic modes, rather than averaging them. The architectural solution to this continuous prediction problem is generative latent variable modeling, achieved specifically via a diffusion process. Meta implemented this through diffusion-based LCMs, specifically testing one-tower and two-tower variants. The diffusion process applied to semantics works by taking an initially noisy input vector and systematically removing noise to identify a clean target embedding. This iterative denoising step is conditioned on the sequence of previous clean concept embeddings that have already been established in the document. Diffusion solves the averaging problem because it allows the model to learn a true probability distribution over the continuous space. With a fully mapped probability distribution, the model can explicitly select and sample one specific semantic future among many. This transition to latent diffusion is the specific mechanism allowing sentence-level autoregression to function. With the mechanics of sentence prediction established, the concept-level architecture can be extended to enable native structural planning. This chart details the LPCM, designed to maintain logical coherence over long-form tasks. It predicts a break concept to define a paragraph boundary. Next, a planning model predicts a plan concept, a summary vector dictating the trajectory of the next paragraph. The subsequent sequence of sentence concepts is then generated based on both the prior context and this explicit high-level plan. Embedding structural constraints into the latent prediction stream allows the model to execute long-form narratives with significantly higher coherence than standard next token systems. Decoupling the architecture in this way results in strong zero-shot generalization across languages. An LCM pre-trained exclusively on an English corpus can generate coherent text in 200 different languages without any additional fine-tuning. Because the core of the LCM strictly optimizes modality-agnostic sonar vectors, it possesses zero awareness of the target output language. Translation occurs by routing the final predicted concept vector through a different frozen sonar language decoder at the final step. Scaling an LCM to new languages or modalities requires only the training of new peripheral decoders. It eliminates the need to inject massive amounts of multilingual data into the core reasoning model. Operating at the concept level also yields an advantage in computational scalability when dealing with long context windows. This graph illustrates sequence length cost. Encoding a 20-word sentence as one concept vector reduces sequence length by an order of magnitude. Transformer complexity scales quadratically, so this compaction minimizes overhead for massive context analysis. The longer the context, the wider the efficiency gap. While current LCMs are proof-of-concept models requiring further scaling, they establish a mathematically viable alternative to the token bottleneck. Replacing discrete cross-entropy with continuous latent diffusion allows a machine to reason in semantic structures rather than predicting character fragments. Large concept models represent a step toward aligning machine generation with the hierarchical reality of human cognition.